Hello, good afternoon, everybody, and welcome to the first live session of this course, Advanced Dynamics. Uh, Let me first thank all of you for joining in this course, and I hope that you are able to follow the course, get all the material, and are able to work through the assignments. Now, it is very important in this course that you work through the assignments, give a thought to it, and try to solve as many problems from the textbooks that are mentioned. We have tried to select a number of representative problems which will try to give you the application of the theory that you have studied in this course, but you have to go through more problems. And in this process, if you have doubts on the lecture material, on the problems, then please write to us on the forum, or this is the time you can write on the chat box or on the Google spreadsheet that was shared with you. So right now this chat box is open. You can always post your questions here. Let me begin by recapturing what we have discussed in this course till now. This is the third week that is running in this course. We started off in week 1 with discussion on coordinate system, which is very important in all of mechanics, as you know. You have to represent points and their motion, particles and their motion, rigid body and their motion. For that, you need to fix a coordinate system. As I have always mentioned, that actually a problem in mechanics can be solved in any coordinate system, theoretically, but then there are choices which will make the solution much simpler. For that reason, we have different kinds of coordinate systems, which we keep using from time to time. And I believe by this time, you must have realized that certain problems are very easy to solve in certain coordinate systems. For example, the pendulum. The pendulum can very easily be solved in the polar coordinate system, but it can also be solved in Cartesian coordinate system, though the equations might be a little more cumbersome. But then in the polar coordinates, it becomes very, very simple. So we have discussed in this course Cartesian coordinates, the tangent normal coordinates, and the polar coordinates, two kinds of polar coordinates, the plane polar coordinates and the cylindrical polar coordinates. And with these coordinate systems, you should be able to tackle problems roughly, any problem in dynamics. And it is very important to realize that the expression of any vector in these coordinates, they have a special form, as we have seen in this course. We have also derived these expressions of velocity, acceleration, etc. And this gives us certain insights like the centripetal acceleration, the Coriolis acceleration, the tangential acceleration, etc. Then we discussed, in the first week, we discussed about relative motion, which is a very important concept, in particular, relative motion in rotating frames. We, as you know, we on the Earth are in a rotating frame. But for most terrestrial problems may not be all, for a large number of terrestrial problems, it is good enough to fix the frame on the Earth and consider that to be an inertial frame. But that introduces errors in if the velocities are large or the distance extent of travel is large, if you have, for example, satellites, for such situations, considering Earth as an inertial frame is incorrect because Earth is rotating, and we have done these calculations. So we need an inertial frame. And why do we need an inertial frame? Because, as discussed in the course, we want to apply Newton's laws of motion, which are valid in an inertial frame. But then we may not always have a convenient frame, which is an inertial frame. It may be a rotating frame. For example, a frame fixed to the Earth is a rotating frame. There are many other instances we have seen. A rotating frame is a very convenient frame to choose. But then we would like to apply Newton's laws. So we have determined the expressions of velocity and acceleration, the derivative of a vector. We have a very special form of the derivative of a vector, which goes as del t, the temporal part, plus omega cross. We have discussed this in great detail in the first week. And we have looked at various problems in non-rotating frames, in rotating frames, and what difference it makes when we go to rotating frames. And in many ways, this expression of velocity and acceleration in rotating frames may be non-intuitive. So it is very important that you follow the proper procedure of vector differentiation when trying to find out rates of change of vectors. And this we have seen in determination of velocity and acceleration. And later in the course, we will also see for other vectors also, like angular momentum. So it is very important to understand this time derivative. So that completed our first week. If you have any question, please post your questions on the chat box. So we now come to the second week, in which we started with particle kinetics. We had about 5 lectures on particle kinetics. And here I have shown you the various applications of these rotating frames. In particular, I would like to highlight what we had discussed. We started our discussion of the path of a freshly painted ball on a rotating disc. If you recall this problem, then you will recall that the path curves. If you look at the trail of the paint that is left on the rotating disc, it is a curved path. And with that example, we discussed how we can understand cyclonic circulations. You see, the Earth is a rotating frame, as I had mentioned, and this is the genesis of cyclones is one example in which you have to consider the rotation of the Earth in order to explain cyclonic circulation. When a low pressure develops at a certain location on the Earth surface, then the pressure falls. So when the temperature rises at a certain location, the pressure falls and the air lifts up. A low pressure region is created because of the localized high temperature. Air from the surrounding regions rushes in to fill this low pressure region. And initially, the motion of the air particles is radial towards the low pressure region. But as it moves, and because Earth is a rotating frame, there is a shift, or there is a change in the direction as we, we see it. And in the northern hemisphere, these particles move to the right, and therefore a counterclockwise circulation is generated. So this we have seen in whenever there is a cyclone, and if you look at the satellite pictures, you will realize this. And in the southern hemisphere, it's just the opposite. And we have discussed this example in this course. So this is one example where the rotation, the non-inertial nature because of rotation is evident, and you have to consider that in order to explain cyclonic circulation. So this was one thing that where we applied the non-inertial frame expressions to explain natural phenomena. There was another example which I have considered, which is the Foucault pendulum. This pendulum was set up by Foucault to show that the Earth rotates. So whenever and recall that all the cyclonic circulation or the Foucault pendulum, these phenomena, the rotation of the Foucault pendulum, plane of oscillation of the Foucault pendulum, these are because of the Coriolis component. And we have discussed the Foucault pendulum again in detail. I have derived the equation of motion, and I have shown how the plane of rotation gradually rotates because of the rotation of the Earth. These are very interesting examples. There are many more examples which are not discussed, but you can look up. For example, if you look at the erosion of banks of a river, then it shows a preferential erosion on one of the banks. It depends on which hemisphere it is in. And this is also because of the rotation of the Earth. As you can realize, when the river is flowing, the water particles are moving in the rotating plane. And that creates this Coriolis acceleration, which eventually it erodes one of the banks of the river more than the other one. You can apply, therefore, these principles now on your own. You can understand these principles and apply them. So this was the discussion, more or less the discussion in the second week. In the third week, we used we started with discussions on the integrals of the Newton's second law. So in the second week, we looked at applications of Newton's second law. And in the third week, we looked at the integrals of the Newton's second law. The first thing that we discussed was the work-energy relation, the work-energy theorem, which is an integral of the Newton's second law. And as I have mentioned time and again in the course, that this will not give you anything new, but it will present the same phenomena in a much simpler light, from where you can very easily deduce or calculate things, because this work-energy relation is an integral of the Newton's second law. So you already have one integral less, you have one derivative less, so it's easier to calculate things, certain things. It is very important to also remember that the work-energy relation is a scalar relation. Newton's second law is a vector relation, which relates the acceleration of a body of a particle with the force acting on it. When you take the integral as we have done in the work-energy relation, we recall that we dot product with the displacement vector, and then we can integrate that. What it tells us is in the most fundamental form is the change in the kinetic energy of a body is equal to the work done by all the forces acting on the body or the particle. In these weeks, we have been discussing about particles. So the change of kinetic energy of the particle as it moves from A to B is equal to the work done by all the forces acting on the particle as it moves from A to B. So here it is about two positions where we are looking at the system, 2 points at which we are looking at the system. We need not consider what happens in between, but we are able to calculate a certain things based on the work and energy relation, which is a scalar relation. And that makes it much simpler than solving separately integrating the Newton's second law. Of course, you will get the same thing. From the work and energy relation, you do not generate anything new that is not already there in the Newton's second law. Only thing is it presents you a very simpler form of the Newton's second law. And then we moved on to the impulse momentum relation, which is again an integral of the Newton's second law. When you integrate it over time, when you take the Newton's second law for a particle and integrate over time, you get the impulse momentum form of the Newton's second law, which is again one integral. So you have one derivative less, and it tells us that the change in the linear momentum is equal to the impulse of the force acting on the particle. This is particularly useful as we have seen later in week 3. You will see in this is the running week. Week 3 is what is running now, and you have you will find applications of this in impact problems. Impact is short duration interaction of particles, and I mean, what we do in impact is when two particles are colliding for a very short duration, we look at the impulse momentum equation in a very short duration. Very short duration, starting from just before the impact to just after the impact. And over this very short duration, what we can neglect is the change in momentum because of smooth forces or continuous forces, which are not impulsive forces. For example, spring force. For example, gravity, which means the weight and other such forces, and also other kinds of forces which can be considered smooth forces, which do not, when integrated over this short duration, a very short duration, actually goes to zero. Their integral of such forces over a very short duration, that duration going to zero, is actually zero. So such forces, such smooth forces or continuous forces, do not contribute in changing the momentum of the particle. Because of this, what happens is, if you consider the total system, say two particles are colliding, if you consider the system of two particles, then the net linear momentum of the system is conserved. So this idea we have used in simplifying problems and solving problems. See, even though weight is acting, maybe spring forces are acting, but then because we are integrating over a very short duration over which these spring forces, the weight, etc., they do not change the momentum of the system appreciably. They cannot change the momentum of the system appreciably. It's only the impulsive forces, the forces under impact, which are impulsive forces, they can change the momentum. And when we consider the system together of two impacting bodies, and because the impacting forces are equal and opposite because of Newton's third law, overall there is no change in the linear momentum of the system. And this idea we have used to solve impact problems. So this was week 3, so which is the running week actually. And I hope you are able to follow the lectures. If not, please write to us in the forum. You can write right now in this chat box, or you can also write in the Google spreadsheet, which was circulated. So please post your questions. In particular, if you happen to be a faculty member of any college, university or institute, and if your students are doing this course, please give us some feedback on how the students are progressing and where they are possibly finding difficulty, and let us also know the standard of questions and the assignments that we are posting from time to time. Every week they have assignments, so please give us some feedback on these assignments and how the students are using this course to understand dynamics. I feel that this course is, the whole course is pitched at the somewhat, as the name suggests, it's an advanced level course. So it is expected that some basic mechanics and engineering mathematics has been done by the students, and this is important in understanding the course further. In the coming weeks, we will be discussing more on particle kinetics, central force motion, etc., orbital motion, orbital dynamics. Then we will be discussing systems with mass flow and system of particles. We'll go over to system of particles, which will eventually lead us to rigid body dynamics. So these are all waiting in the future weeks, and I hope that the students are enjoying, you all are enjoying, all those who are participating in this course, you are finding it useful. If there are any difficulties, doubts, please post on the forum. I have received one question, though it's an incomplete question, from Mr. Seshu, K. Seshu, in the Google spreadsheet. He's a student, but the question happens to be incomplete. So, Mr. Seshu, if you are live, then you can submit the question here. Okay. So now I will start taking the questions that have come up in the chat box. Rafael Shaikutinov, he says hello. So hello, Mr. Rafael. Rafael, you have done my previous courses, and I remember you. Here you are saying, could I write to you with some questions about another course, kinematics and dynamics and of machines? I have a parallel robot where two hands are connected to object that moving in a rectilinear way. I tried to calculate it with the methods we covered in the course, but I have had a difficulty. With general coordinates, can you suggest for this problem? Okay, so there are a number of points which Rafael has brought up. I will go through them one by one. Definitely, you can write to me about problems related to dynamics. You can send me email. You can contact me over email. You can contact me on the forum as well. If you're doing this course, you must have access to the forum, and you can post your questions there. I will try my best to answer or sort out, even if it is from another subject. Like you mentioned that you have a parallel robot. where two hands are 3R, so connected to object that is moving in a rectilinear way. So I believe so here I think you'll have to wait a little bit, because what I feel is rigid body dynamics might be relevant in this case. So when you come to rigid body dynamics, then I'm sure you'll be able to take up this problem, analyze this problem. Then there is another question by Rafael: when we can expect your vibration course again? This may take some time, so that I cannot immediately commit. This may take some time. Then Rafael also mentions, is it known nowadays how to solve Timoshenko plate problems? I found in your book only beams, but is this type of problems solved already? So you can define the eigenvalue problem. Of course, this let me mention here that this course is on rigid body dynamics, but the questions that are posed by Rafael are they relate to structural dynamics, so deformable body dynamics, and the eigenvalue problem can be defined, of course, but exact solution, I mean, you'll have to use some limits. So that is what I can say for the moment. So exact analytical results of general result for the eigenvalues under certain approximations, it is possible. Okay. Why? So there is another question: why the guy in the session of your advanced mechanics course is using different notation? It seems like he considers problem of his own interest, and they wouldn't help assignment problems. Okay, so there is one. I understand now what Rafael is saying. There is a tutor, and possibly he has used a different set of notations. But Rafael, I think if you understand the concepts, then notations can vary from person to person. Like from book to book, notations can vary, or the style of presentation can vary. I suggest that if you have any difficulty with the notation, please write to us in the forum, and we'll try to sort out. Because immediately the tutor who possibly is taking classes on Saturdays or some other extra time, he's in some other place. We'll try to get to him with these points. But right now, my suggestion is, if you have any difficulty, please write to us in the forum. You can write directly to me to my email address, which you have done previously also. So please contact me through email, through the forum, and I'll try to resolve your questions. I hope I have been able to answer your questions. Do write to us how you are finding the course. This is for everybody, and Rafael, also to you. If you please write to us on how you're finding the course, if you have specific feedback or difficulty, as you have mentioned already, and I also have answered, you can post your questions in the forum directly, and we'll try to reply to you. You can also directly contact me. So you're welcome. So I don't find other questions immediately in the chat box. So I guess that I have more or less answered the questions. Now Rafael has come up with another question. No, I have vibration course done. There were problems with the payment. So I'm going to take it again. Thank you. that you remember me. Okay, and thank you for joining, Rafael. It is a pleasure to have you in this course. There is another question from Satish Kumar. Can point particles have rotation aspects of dynamics? Rotational aspects of dynamics. So point particles, when we say point particles do not have dimensions. There is no dimension. It has only mass. It doesn't have any dimension. If it doesn't have dimension, it cannot have inertia, rotational inertia. It can have translational inertia, but it cannot have rotational inertia. Something that doesn't have rotational inertia, and because it doesn't have dimension, you also cannot apply torques to it. You cannot apply torques. So rotational dynamics rotational dynamics for a point particle is a meaningless question to ask. That question is not well posed, or it cannot be posed rather. So rotational dynamics for a point particle cannot be posed. We completely drop out the orientation part of a point particle. After all, you think about it, how do we know rotation? We know rotation when we can draw a line on a body and look at its orientation. In a point particle, we cannot draw a line. We have no way of tracking its rotation also. So theoretical point particles, for that, we do not worry about rotation or rotational dynamics. It's only, but then are point particles realistic? Well, no. Point particles are not realistic. But then, as we will see in rigid body dynamics, for rigid bodies, there is one part which is taken care of by the translational equations of motion. The translational equations of motion are the equations of motion of the center of mass of the body. This we will discuss when we come to rigid body dynamics. Only to that we apply Newton's second law. Then we have the Euler's equation for the rotational part. So strictly for a point particle, we do not worry about rotational dynamics. It's only for rigid bodies that we have rotational dynamics equations. So I hope I have answered your query that point particles do not have rotational aspects of dynamics. Okay, I think I have taken many questions, and we'll close down the session now. I would like to thank the NPTEL staff of IIT Kharagpur for making this possible. And I would like to thank all the TAs who have helped us in this course, who are helping us in this course. And I also thank all the participants of the course for being with us. So thank you.